Alrighty, so we've been talking about friction. We've been talking about forces. All of the forces up to now have been horizontal, right? All the pushes, all the pulls have been horizontal, with the exception of the ones where it's top down from like north and east or second, right? Well, today we're going to look at ones that are at an angle. Okay, so after this, you'll be able to calculate the horizontal component of an applied force that's applied at an angle and use it in F equals ma. So it's really just taking what we know, taking one step back, adding one more step. I keep adding one more step to the process. So we're going to show our work. Okay, now right away I spot something that I'm trying to get rid of. Because I've realized over the years, I'm going to fix this right now. It won't appear on the solutions, but FH, I'm going to write this, maybe this might help. Let's do it this way. I'm going to write in here, FH. All right, let's do that. Okay. So we've got this applied force, which is applied at an angle, some angle. And then what we have is this component, this portion of the force that is applied horizontally. Now, what I've done out in the past is called it FH for horizontal force. But what I think I've realized that it might lead to better understanding of other things is I'm going to be calling it FAX. So it's the X component of the applied force. And the reason that I'm switching to this is kids weren't realizing that FH was part of FA. They thought it was a different force, and it's not. It's simply the X part of the applied force. Okay, does that make sense? See, it's the part of the force that's actually pulling it sideways. Now, another unit coming in your future, but there's also this one right here. What is it? It's going to be FAY. It's the Y component of the force. The part of the force that does what? Lifts it up or pushes it down, I guess. Okay? More on that in a bit. Okay, so, and that's kind of the intro. That's kind of the whole basic. Let me sort of review that now using some more terminology and go more in depth. So in a situation like this, not all of the applied force goes into horizontally the object. Sorry, goes into accelerating the object horizontally. Not all of it. Right? And again, as always, don't feel like you have to write everything down. Like, please don't draw the picture again. Right? So FAX is the part of the force that is accelerating it horizontally. Only the horizontal component acts horizontally and contributes to its acceleration. Right? This is a good lead-in for grade 12 projectiles, unit 2. The value of the FAX, or the FH, is dependent upon the applied force and the angle. Because if this angle is more like this, then what happens to, oh, I got to move it all down here, don't I? If it's steeper like this, what happens to the amount of the FAX? Well, it's shorter, isn't it? Right? And that sort of makes common sense, that if you're pulling up at a steeper angle, it's not going to go as fast sideways, right? In fact, if you're pulling up at a steep angle, you're doing more lifting than you are pulling sideways. Okay, make sense? And obviously, if you pull more, if you've got a greater applied force, well then you've got a greater FAX. I'll pause for a second there in case you want to write anything down. Okay, so there's that picture again. Please don't draw it again. Suppose that the applied force FA is equal to 100, and the angle is 30 degrees above the horizontal. Okay, so we've got 100 newtons here, we've got 30 degrees right here, and so my horizontal, or my X component, we're going to use good old-fashioned grade 9 trigonometry. You probably said, oh, when am I ever going to have to use that again? You're wrong, right? Okay, so this side here is the adjacent, right? It's adjacent to the angle. And this side here is the hypotenuse. Which one has hypotenuse and adjacent in it? Our old friend cosine. Right? friend cosine. Cosine is adjacent over hypotenuse, so the adjacent is my FAX or my FH. And my hypotenuse is 100. Now, we've had some issues in the past about solving little things like this. That has to become second nature. How do we solve this? Multiply both sides by 100. That side cancels, and you get FAX is equal to 100 times cos 30, or 86.6. Is the value of the horizontal component always going to be less than the hypotenuse? That says yes. Is the horizontal component always going to be less than the hypotenuse? Yes. Absolutely. Right? And in fact, the smaller the angle, right? Like if this is maybe down here, like 10 degrees, then what does that do to the FAX? It's going to actually make it longer, right? Tough for me to keep it the same length. There it is there. It's actually going to be longer. And if it's steeper, well, then it becomes, right, not S, right? So 30 degrees, yeah, it's about 86.6. Okay. If the angle increases, say, to 60, there I go. I'm getting ahead of myself. The angle increases to 60 degrees, then the FH will also increase. If you need to write this down, yeah, it's up to you. Will decrease. Did I say increase? Decrease. Force of 100 newtons is applied at an angle of 30 degrees above the horizontal to a 25 kilogram sled. Determine the acceleration if the surface is frictionless. So let's draw that free body diagram, which you're going to draw right away. Now, just hold on. Right? Just watch for a second. Right? So I've got my FA is equal to 100. Right? My angle here is 30 degrees. My mass is 25. Is there any friction? No. Okay, so I'm needing to find the acceleration. Well, F net is equal to ma. Do I have the net force? I guess I should maybe put weight force and normal force in there, right? But again, they are balanced, and so we're not going to worry about them. And when I say balanced, I'm kind of glossing over a fact there, but you're going to let me go ahead with that. You're not going to call me out on it in about a week or two. So the only real force that matters is this FAX, right? This X component, horizontal component. So we're going to find that. We're going to set that equal to our F net. And then we're going to find the acceleration. How many steps are we talking here? 3? This is the last one. You got to find, well, FAX is equal to F net. Is that a step? I guess it is a step, sure. Okay. So we're not going to do any calculations in that step, though. Okay. When Carter comes back, then... Okay, let's just do these steps here. Or do you want me to let you do it? You try it. Okay, let's have a look here and see what this looks like. So we're going to write cosine 30 is adjacent FAX over the hypotenuse, which is 100. I think this is exactly the same numbers we had before, is it not? 100 cos 30. It's not. Is it not exactly the same? It's exactly the same. 86.6. Notice how I'm showing my work, kind of lining up my equal signs, putting it as a sort of a little step on its own, and then I'm going to write F net is equal to FAX. So the net force is 86.6, and then it's a simple matter of going F net is equal to MA, and my 86.6 goes in for my net force. The mass is 25. How do we solve that? Divide both sides by 25, and A is equal to, somebody help me out. 3.46, 3.5 then we'll say. 3.5 meters per second. Now, it's an acceleration, so it's a vector, so there should be some direction involved. are the words north, south, east, or west in the diagram or in the question? No. So all we know is we don't really have anything to sort of mark it relative to. We're going to assume the 100 is like this to the right. It's positive. We're just going to leave it at 3.5. It's positive. The direction is kind of immaterial, really. We're not given enough to work with in the question. So again, all I did was introduce this idea of a horizontal component. What do you think the next question has? I'm going to probably take it one step farther. I'm thinking there's friction involved. What step is that going to affect? The F net, right? We're going to introduce friction in there. Force of 50 newtons is applied at an angle of 15 degrees above the horizontal to a sled having a mass of 30 kilograms. If the friction force is 5, determine the acceleration of the sled. Think you can do it? I think so. I've given you the steps, exactly the same steps. You're just going to have friction in here. Okay, you give it a whirl. There's plenty of room there if you make a mistake. And of course, you're all working in pencil, so let's draw a picture. Is the picture important here? Yeah, it's pretty important. I mean, after a while, you sort of, oh yeah, I've done this. You get the picture in your head, really. Right, so we got 50 newtons, we got 15 degrees, got a weight force, we got a normal force, but they're balanced, so we don't really care about them. And we got a friction force here, right? So step one is to solve for the x component, sideways component, and it's going to be, now, is the FAX always going to be the cos? You hope so. Cosine is always adjacent and hypotenuse. Well, the hypotenuse is always going to be the applied force. Is the adjacent always going to be the FAX? 99.8% of the time, yes. When the angle is above the horizontal, well, then the horizontal component is going to be adjacent to that, right? The only time it might not be is if you're not given the angle like this, but you're given the angle like that, which would be 30 degrees from the vertical, right? So if they give you the angle as from the vertical, well, then the horizontal component here is going to be opposite, and it's going to be sine. But 99.8% of the time, it's going to be equal to the cos. So if you want to adjust your formula so that it says FAX is equal to FA times cos theta, I'm okay with that. If you understand that it's not always going to be cos. It's completely dependent upon the angle being that one there. But again, 99% of the time, that's what it's going to be. Okay? Nod. You just click the little agree box at the end of the service agreement or whatever you want to call it, right? You agree? Okay. You can't hold me to it. It's going to be always. So this is going to be 50 cos 15 48.3. Okay. No. Well, basically what we're doing is we're doing this. Don't write this down. Just watch. Cos theta is equal to adjacent, which is FAX, over hypotenuse, which is FA. So what I'm really doing is that multiplying both sides by FA prior to putting the numbers in. So I get FAX is equal to FA cos theta. So I'm rearranging the formula before putting the numbers in, which is a skill you need to sort of eventually get. I just don't encourage it at this stage yet. Okay, so we got 48.3 newtons. Now before, the net force was equal to the FAX, but that's not the case here because now we have friction. So you would write F net is equal to FAX plus FF. Those are the two forces that are acting sideways. So that's going to be my 48.3 plus minus 5, right? You're going to subtract the friction. The horizontal component is reduced by friction. So instead of 48.3, it's going to be 43.3. And now what? Now do the last step again. See how I'm kind of building it all together here for you? Divide both sides by 30. $1.44. Hard? A little different, a little new. That's all. Okay, let's have a look at example number 3. A man is pulling his 50-kilogram son. He's a big boy. Maybe he's wearing a wet snowsuit. On a 15-kilogram sled across an ice surface with a friction force of 2 newtons. The rope makes a 30-degree angle with the horizontal. He applies a 250 newton force on the rope for 3 seconds. Find the final velocity of the sled and the distance it travels in 3 seconds. So all I'm really doing, I'm adding the step of going into kinematics, and we're trying to find the distance, right? So basically we're going to do exactly this, and then once you get your acceleration, then you're going to do the stuff that we did in the previous unit. Let's draw a picture. Do you see how it builds? It's like Shrek or Parfaits. $30 degrees, we got friction. Oh, friction's only 2. That's because it's on snow, I guess. All right. Step 1.
Add the mass.
Oh, yeah, well, you got to add the masses, right? Well, do we need that just yet? We can do it first if you want. Do we need to even show that? Can we just write mass equals? Oh, yeah, right? Because the mass, yeah, so you got to add those together. So the mass is 65. Why do I throw in those little things? Give you another opportunity and a mark, right? Oh, a pretty easy one. Okay, so now we're going to find our x component. So FAX is equal to. Did you realize I'm kind of talking to a whole bunch of other people? Carter's sorry that he interrupted you there, so you probably didn't hear him because he whispered it. FAX is equal to FA cos theta. So this is going to be applied force 250 times the cosine of 30. 250 times cosine 30. Make sure you're in degrees. 216.5. Is that a reasonable answer? Makes close sense, right? It's going to be a little less than the hypotenuse. Now what? Don't know. What did we do before, Riley? It's right here. Just look back. You don't have to remember. We're going to find the acceleration, but first we got to subtract friction. F net is equal to FA plus FF. Let me write that again so people can read it. So 216.5 plus minus 2. Hopefully you don't need a calculator for that. We'll get there. So F net is equal to MA. 214.5 is equal to 65A. Divide by 65. And you get an acceleration of 3.3. 3.3 meters per second squared. So now we're at acceleration. Now we got to move into our kinematics formulas. We want to find the final velocity of the sled and the distance it travels in 3 seconds. The final velocity, the VF. It didn't say, come right out and say it, but generally 50-kilogram boys start on 15-kilogram sleds at rest. They just sit there, right? So the VI is 0. So I'm going to go A equals delta V over delta T. 3.3 is equal to change in velocity. What was the time? 3 seconds. Change in velocity, 9.9. Multiply, right? We're multiplying by 3. Multiplying by 3, Riley, right? Okay. Now, because the VI is 0, that means, therefore, that the VF is 9.9. If you want to write that out and show that, you can, but, right? How do I find the distance traveled? V bar equals D over T, but do I have V bar?
Yeah.
Got to find the average. Now, fortunately, it's one of them is 0. So 9.9 all over 2. Basically, it's 9.9 divided by 2, right? 4.95, of course. Holy. Multiply by 3. Whew. I was just waiting for that question to come. 1, 2, 3, 4, 5, 6. Round up to 8. Are they going to get any harder than that?
Probably, yeah.
Not this unit. That's about as hard as they get. And really, the last 3 steps, right? Okay. You can now do on that very first page that I gave you way back on Thursday, almost a week ago. There was 2 questions, number 7 and 8, that said horizontal, so you can now do those. And set 2 on the back side of that, number 2, has one more problem. I should probably try to come up with a couple more. The question sheet that you got today, according to students, is the questions are a little more challenging, but there are no horizontal questions on it. So I can probably run a little bit more of those. Okay? So I'm going to give you, very generously, I'm going to give you the rest of this period. Okay? And then we'll be moving on tomorrow.
How many pages do you left?
Not a whole lot, really. I got to do a lap. All that's really left is to do a lap.